Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at endpoints of intervals, specifically in calculus. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight we're really lucky to be joined by our two panelists, Vicki Carter and Steve Kokoska. Vicki has been teaching high school math for 42 years and currently serves as the math department chair at West Florence High School. She's a former co-chair of the AP Calculus Development Committee and served as an exam leader at the AP Calculus reading in the summer of 2018. She received the T-Cube Leadership Award in 2015 and has served on TI-Nspire authoring teams and presented at many national, state, and local conferences. Vicki, thanks so much for joining us tonight.
Yes, it's a pleasure to be with everyone.
And Steve is a professor in the Department of Mathematical and Digital Sciences Department at Bloomberg University. He recently completed his term as chief reader for the AP Calculus reading and as a member of the Development Committee. Steve is an active T-Cube instructor and College Board consultant with recent workshops in China and Singapore, and he just published an AP Calculus text. Steve, so great to have you with us tonight.
Thank you, Michael. Thanks for having me. Thanks for arranging this.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions for Steve or Vicki using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate at the very top of the WebEx menu and choose Audio Broadcast. At this point, Steve is going to discuss our agenda.
Thanks, Michael. Well, we've already had some welcome and introductions. I'm going to talk for a while about, in general, the analysis of functions. And specifically, I'm going to address the intervals on which a function is increasing and decreasing, and on which it's concave up or concave down. And I'm going to look at those endpoints. There have been a lot of questions about the endpoints of those intervals. And then I'll eventually get to talk about inflection points, and I will somehow put this all together and talk about AP exam scoring, and specifically one of the free response questions that involved a part about inflection points. And then when I'm all done, I'll pass the screen over to Vicki, and she'll talk about some TI-Nspire technology activities, how to use technology to do some of the things that I talk about content-wise.
Thanks so much, Steve. And Vicki is going to discuss our expected outcomes.
Tonight, we hope everybody will get a better understanding of how to write these intervals on which a function increases or decreases and compare that to the intervals that we use for concavity. We're going to talk about inflection points and, of course, endpoints of an interval. We're going to talk about what we expect to see on the AP exam, although this is also pertinent to any calculus classroom. As Steve said, he will share some insights on that recent question that had a lot of discussion this past summer. And then we're going to talk a little bit about technology and also correct vocabulary and language that should be used in the calculus classroom.
Vicki, thanks so much. Steve, you have control. Feel free to share your application.
Okay, I'm going to give that a shot. Here we go. Beautiful. How's that, Michael? Can you see that?
Looks good here.
Okay, thanks. So as we were saying, Mike, Vicki, recently there's been a lot of discussion on the AP Calculus Facebook groups especially about endpoints, and specifically the endpoints of intervals in which a function is increasing or which is decreasing, and the endpoints in which a function is concave up or concave down. And it seems to me from what I've read that a recurring question is, do you include the endpoints in any of these intervals, or do you exclude them? So what I'm going to try to do is I'm going to try to answer this question in two different ways. And first, I'm going to approach this very mathematically for any calculus course. And I'm going to give you what I believe to be the correct interpretation, or at least a correct interpretation. And then eventually, I'm going to connect this with how these intervals are scored on the AP Calculus exam. So I'm going to ask you to bear with me here, as I might have to give you a little bit of background information. So let's start by talking or taking a look at increasing and decreasing. And to answer these questions about endpoints, for me, mathematically, what I need to do is go back to the definition. So here's the definition for what it means for a function to be increasing or decreasing. So for example, a function f is increasing, notice, on an interval I, if for any values x1 and x2 in I, so that x1 is less than x2, the value of the function at x1 is less than the value of the function at x2. So as we move from left to right, the value of the function is getting bigger. Now, I'm not going to read the other one to you, but notice that these definitions involve an interval I. I think that's important. Now, once we have these definitions, then we can use this increasing and decreasing test to help find these intervals on which a function is increasing or decreasing. So down at the bottom of this page, I probably should have called this a theorem, and I know it's a dirty word, but we could probably even prove this if we wanted to. But at least part of this says if f prime of x is greater than 0 on an interval, then f is increasing on that interval. And I think there's two important things to notice in this increasing-decreasing test. First, once again, it's addressing an interval. And the second thing is, notice that this doesn't address what's happening or what's going on here when f prime of x is equal to 0. So let's try to take these definitions and let's try to apply this to an example. And as we work through this example, let's look specifically at the endpoints. So here's a function f, a polynomial, and let's see if we can find where it's increasing and where it's decreasing. Now, as I work through this problem, I understand that there are some other calculus concepts involved in this problem that I didn't define here. For example, like extreme values. So I understand there are other things going on in the background, but remember, I'm specifically focusing on endpoints here. So here's a way that I would solve this problem analytically in my classroom. First, I'd find f prime of x, and what I try to do is to factor that completely. And what I'm going to do is I'm going to look for what I call candidates for extrema. And these are places where the first derivative is 0, or where the first derivative does not exist. So for this problem, since I have f prime completely factored, I can see that f prime of x is equal to 0 at -1, 0, and 2. And it sounds kind of funny, but the way that I say this is there are no places where the first derivative does not exist. Now, in my class, I construct a sign chart. And I'll probably repeat this again tonight, but remember that AP Calculus students can certainly use sign charts, and I think this is a very valuable mathematical tool. But right now, this is not sufficient justification on the AP Calculus exam. An AP Calculus student has to interpret a sign chart if they present one. So on my sign chart, I draw a number line with tick marks at the candidates for extrema. And in this example, above each of these candidates, f prime of x is equal to 0. So for example, f prime at -1 is equal to 0. Now, next I determine the sign in each one of these intervals, the sign of f prime. And I know that some of my students like to pick specific values in the interval and evaluate f prime of x, and that's fine because we know that f prime of x cannot change sign in an interval. And others, like me, like to argue in general by looking at the factored form of f prime. and, for example, say, suppose I take a value of x that's to the left of -1, like large negative. In any event, now I have the sign of f prime in each one of these intervals. And using the increasing and decreasing test from the previous slide, I add some arrows to indicate the behavior of f. Those arrows are sort of in that bottom row of my sign chart. I know that on each one of those intervals, I know now whether f is increasing or decreasing. And now I'm going to put all of this together. And I've concluded that f is increasing on the closed interval, -1 to 0, and closed at 2 to open infinity, and decreasing -∞ to -1 closed, and closed 0 to 2. I include these endpoints in these intervals because if you think about the definition of increasing and decreasing, certainly the function f is increasing on that interval -1 to 0 closed. As x moves left to right, the value of the function f is certainly increasing. Now, I've been in several discussions recently in talking about this where someone will say to me, well, look, 0 is included in 2 different intervals, and so that's a contradiction. And I don't think it is. I don't believe it is. And the reason is because increasing and decreasing are defined on intervals, not at specific values. So, in my opinion, this is not a contradiction at all and is correct mathematically. So here's a bottom line, and I'll go through this again, but for now, here's a bottom line. I believe that endpoints can and should be included, where possible, where appropriate, in the intervals on which a function is increasing or decreasing. However, on the AP Calculus exam in general, endpoints don't matter. That means that a student can include them or exclude them unless the function is undefined at an endpoint and the student includes that value, then it would be wrong. Or they write infinity or negative infinity as part of a closed interval. So what about concavity? Well, once again, in order for me to reach a conclusion here, I believe I need to go back to take a look at the definition. So let me look at least part of this with you. Suppose f is a differentiable function. F is concave up at A if the graph of f is above the tangent line to f at A for all x in a neighborhood of A, but not equal to A. And there's a similar definition for concave down. Now, notice the difference in this definition when we compare it to increasing and decreasing. This definition is given in terms of a specific value, not an interval. So a function can have or has concavity at a value. That's kind of an odd concept. This definition, again, is given in terms of a specific value, not an interval. Now, here's a couple of visualizations of this definition. I like these. On the left-hand side, the function is concave up at x equal a. And the reason is because I can draw a tangent line to the graph of f at x equal a, and I can find a neighborhood about x equal a. And by the way, that neighborhood doesn't necessarily mean a symmetric interval. And the graph of f is above the tangent line in that neighborhood. So it satisfies the definition. Now, notice one other thing. I'm not going to talk about this formally, but I know we use this a lot, especially in AP Calculus, especially on the exam. And that is, as we move left to right in this function, as x increases, f prime of x is increasing. And so we often use that as a definition or as a similar theorem to the increasing and decreasing test. If f prime of x is increasing on an interval, then we know that the function is concave up. Now, similarly on the right-hand side, the graph of f here is an illustration. It is concave down at x equal a. And the reason, once again, is I can draw the tangent line to the graph of f at x equal a. And there's a neighborhood of x equal a where the graph of f is below the tangent line. So again, it's concave down at x equal a. Now, there's one other important case here, in my opinion. So take a look at the graph of this function f and the tangent line at x equal a. In this case, I can't find a neighborhood of x equal a in which the graph is always above or always below the tangent line. And therefore, in my opinion, we say here that f has no concavity at x equal a. I'm going to use that here, especially as I get towards the end and talk about the free response question. So bear with me. Let's take a look at one more example and try to apply this definition. And again, I understand that there are some other mathematical concepts going on in the background here that I did not formally define. For example, inflection points. And I'll come back to that in a minute or two. So here's another polynomial. And let's see if we can find the intervals on which this function is concave up or concave down. And while we're here, let's see if we can find the inflection points. And loosely stated, those points on the graph where the graph of f changes concavity. And again, I'll show you my formal definition of an inflection point in a minute. Now, I'm going to analyze this function for concavity in a similar manner. So I'm going to find the first and then the second derivative. And I'm going to find the candidates here for points of inflection. And these candidates are places where the second derivative is 0 or does not exist. And so once again, I'm going to draw another sign chart. And I'm going to put tick marks on this sign chart at the important points. To me, those are candidates for points of inflection. Now, by the way, there are all sorts of other possibilities for sign charts here. Places where the second derivative doesn't exist, places where the function is not defined. And I think I've done enough of these problems that I have a way to represent all of those cases on my sign charts. So in this sign chart, I have tick marks at 0 and 2. Those are places where, in this case, where the second derivative is equal to 0. There are no places where the second derivative does not exist. And I've gone through here and marked the intervals as positive for f prime of x or negative. And again, I can plug in a specific value of x into f double prime or argue in general. And I know because f double prime is positive, I know that f prime is increasing. I know the function is concave up on two intervals there and concave down in between. So my conclusion here about intervals is that this function is concave up from minus infinity to 0 open and 2 to infinity open, and concave down from 0 to 2 open. I don't include the endpoints here, and the reason is because at x equals 0 and at x equals 2, there is no concavity. It's not concave up, it's not concave down. Concavity is defined at a value. And so I wouldn't include those in either one of these intervals. So putting a lot of this together, here's a graph of this function f, and I marked a couple of points on this graph. I marked the inflection points. I believe those are at 0, 0, and 2 minus 16. And you can almost see that those are changes in concavity on this graph, changes where the graph changes from concave up to concave down or vice versa. And I included one other point on this graph. I think it's 3 minus 27. There's where the absolute minimum value of this function lies. Now, I believe Vicki will talk a little bit about using technology to produce this kind of graph and to use technology to find these points, these important points. So let me see if I can summarize so there is no misunderstanding. Here's how the AP Calculus exam is scored with regard to these concepts. You know how I stand on these. Bluntly, I would include endpoints where appropriate when I'm talking about increasing and decreasing. I do not include endpoints in concavity. So inclusion or exclusion of the endpoints on the AP exam don't matter unless there's a contradiction. A sign chart, remember, is not sufficient justification, but parenthetically, you know what? It's still a very good mathematical tool. Written justification, confirmation of the sign chart, or maybe I should have said there, interpretation of the sign chart is necessary in order to receive credit on the AP exam. Now, one aside here, this is certainly how I approached this when I was chief reader and grading the exams, and I believe this is how the current chief reader, Stephen Davis, approaches this. But Julie Clark will be taking over in 2020, and we don't know whether or not she will keep things the same. So the grading of the exam may change slightly, but for now we're still going according to that famous sign chart document. So to sort of tie up at least one loose end here, here's my definition of an inflection point. Here's the one that I use. So a point P on the graph of F is an inflection point. If F is continuous there, and the graph changes from concave up to concave down, or from concave down to concave up. And here's a couple of conclusions that I think I can draw from using this definition and the previous concepts. So I know that if F double prime of A exists and it's not equal to 0, the concavity is known. The graph cannot change concavity there. F double prime of X can only change concavity where F double prime of X is equal to 0 or where it doesn't exist. So for me, I get an inflection point only where the second derivative changes sign, and I can use a sign chart for the second derivative. So I guess you've already seen this, but here it is in writing. Here's my procedure that I would use in class, my college calc class, for determining inflection points. Find the IP candidates, and these are the values of X in the domain of F, so that F prime of X is equal to 0 or F double prime of X does not exist. And I'm going to screen these candidates. I'm going to check for a change in the sign of F double prime at each one of these candidates. And if a change in the sign occurs, I know I have a point of inflection. And if there is no change in sign, well, then darn it, I don't have a point of inflection there. Now, how does all of this apply to the free response question from last year's exam, which generated a lot of talk, a lot of good discussion? So this was AB3, BC3 from the 2018 AP Calculus exam. We're given the graph of a continuous function g, the derivative of the function f. The function g is piecewise linear, well, with part of a parabola on the right-hand side. And at this time, I'm really only interested in part D. And that says find the x-coordinate of each point of inflection on the graph of f. Now, let's try to think about this question in the context of the definitions and the examples that we've talked about this evening. We need to find places where the graph of f changes concavity. That is, from concave up to concave down, or from concave down to concave up. So, for example, let's consider and remember the function f on the interval -5 to -2. Now, remember, what we have here is a graph of f prime. This is the derivative of f. Now, since f prime of x is equal to -3, a constant, that means f double prime is equal to 0 on that entire interval. And that means that in the definitions, in the context of the definitions that I gave you this evening, there's no concavity at any point in that interval. And to try to visualize this with an air diagram, think about a straight line with some positive slope, for example. A straight line has no concavity at any value because, pick a point on that line. I cannot draw a tangent line that is either always above or always below in a neighborhood of the value. So going back to this problem, for the interval -2 to -1, the function f prime is increasing. So f is concave up on the interval -2 to -1, open at both endpoints, but there's no change in concavity at x equal -2. The function the function f did not go from concave down to concave up. In some sense, it went from no concavity to concave up. Now, I won't make these arguments in detail, but similarly, there is no change in concavity, for example, at x equal -1 or at x equals 0, or at x equal 1 or at x equal 3. Or there's no change in concavity at any value of x between 1 and 3. And so the only point of inflection here occurs at x equal 4, because that's where the function f is concave down to the left and concave up to the right. And here's a quick look at the standard for this problem. There was 1 point for the correct answer, only x equal 4. And there was 1 point for the reason that f prime of x changes from decreasing to increasing at x equal 4. Now, notice something here about this scoring standard. A student cannot say that x equal 4 there is a point of inflection at x equal 4 because there's a change in concavity there. That's really the definition of an inflection point. And in order to receive credit here, in general, what we need to do is to use the information given in the problem as justification. Okay, I think I've gone over my time limit. Sorry about that, Michael, but I do hope that that helps a little bit. And I'm going to try to turn it over to Vicki now for a little technology intervention.
Thanks, Steve. I really appreciate that.
All right, there we go to Vicki, I think.
Okay. So when I was teaching this unit this year, I tried to think of some things that might actually help the students understand what we were going to accomplish. I've always liked this document that is called Derivative Analysis, and one of the things that I want to make sure students understand is what do we really mean by increasing, decreasing, because I can talk about as I move from left to right on the graph, it's like I'm moving upward or moving downward, but sometimes I realize students have difficulty actually interpreting that as far as a picture, a graph, and concavity can also be a little bit difficult. So I like to work through this document first. All of these documents will be shared with you. So, and this one's also on the TI website under the math-inspired calculus version. Basically, you are going to be given a F1 of X, and you can define your own, but there's some really nice ones here to work with. And we're going to move a point X along the X-axis, and it's going to display positive and negative slope. This is a pretty nice little document. So when I go to page 1.2, And the way that I move to this next page, I just clicked on it then, but I'm on a handheld, I need to press Control and the right arrow, and it will move to this page. And what I like to do is talk with the students about what we observe. A lot of times I'm demonstrating this in front of the classroom while they're following along on their own handhelds. And this might be a time that I say, stop. I want everybody to watch what I do, and then I want you to explore. So if you will observe in it's not exactly the upper right, but somewhat the upper right, right now it says the slope is positive. You can see a part of a tangent line, and we have a draggable point here. It's like an open white circle on the x-axis. And what I'm going to do is grab that point and drag it across from left to right. And so we can see that the slope is positive, and then there will be a place in here where the slope is negative. And so what I'm trying to get the students to do is to make an association with increasing with slope positive and decreasing with slope negative. And so we may just explore this document for a few moments and talk about those different aspects that we're seeing here. Now, what the students really like to see is that if I go to the next page, so I'll press Control right. So now we're going to actually analyze the sign of the first derivative, and we're going to have some little slider arrows that will help us here. So let me go to this next page. And they're not really, I call them clickers. The screen said slider arrows, so I like to call them clickers. So we've got little clickers here in the upper left, and if I click, say, the upper one, so I click up, what it does is displays those intervals over which the tangent line had a positive slope and tells them that this is where the slope was positive. Now it becomes very clear that they have that association, hopefully of increasing as I move across the graph from left to right with a positive slope. If I click the down arrow and down arrow one more time, now I will see where my slope was negative, and they will have a visual connection to when the graph is decreasing. So let's look a little bit more at this document. So I'll go to the next page. And now we're actually going to be able to explore a little bit about concavity. So again, I'm going to move my open dot across the screen. Of course, I have the little southern saying of concave up like a cup, concave down like a frown. And then we have concave up. And then we have concave down. Now, notice there's really no connection to slope right now. I've got another document that might help with that a little bit. This is just to get an association of concavity. When is the graph concave up? When is the graph concave down? We have a similar screen in which we can click on the little clickers that will show us concavity. So I'll click here. My students are actually kind of fascinated by the fact that it could show this. Now what I did is I was on a smart board or some kind of interactive whiteboard, and I put little dots here on my whiteboard, here and here, and then I removed the concave up and went to concave down, and then it was those same dots were at the end of this interval, and so then we could talk a little bit about the points of inflection where the concavity was actually changing. So, Steve, do you want to add anything to that?
Thanks, Vic. It looks great. I like this activity also. It's very nice. Okay.
All right, so let's look at the next one that I typically use with my students, and it's the one called First Derivative Test. For this one, I actually share with the students the paper document, and we go through and do that. And I think it is very valuable for the students to work through that paper document. I'll show that to you in just a second and tell you why. But again, we're going to have some arrows, or we can grab and drag the open circle on the x-axis and see some changes here. So let's go to this next page. I can either click on these clickers here, or I can drag this open dot. I think most of my students preferred to drag the open dot. But we see a tangent line here, and so we see that the tangent line has negative slope. So now we actually have a value for slope, not just saying that it's negative. And so we have negative slope, and if you are really good, you can make it show up with a slope of 0, which of course is a valuable thing to talk with the students about. And now we have a positive slope. And so on the paper document, what the students are actually supposed to do, and this is called the first derivative test, it goes along with that document. They define a critical point. We call it a critical number in my class, but it is called both in many different textbooks. And so what they're actually going to do is they navigate through these pages. We just explored page 1.2. There's 1.2, 1.3, 1.4, 1.5. They actually say what the critical point is and why it's a critical point. Is it because the derivative was 0 at that number, or was it because the derivative was undefined at that number? And then we identify it as a local min or a local max or neither. And then we start talking about what's going on. Where was the slope of the tangent line positive? On what intervals? Where was the slope of the tangent line negative? On what intervals? I found it kind of interesting, but this next statement down here says, summarize your findings for the 4 graphs. My students really couldn't summarize. They really didn't know exactly how to summarize what they were seeing. There's another set of questions with another document, and when they got through it, it was kind of cool. They all came back and said, oh, we know how to answer that question on the first page now. So I felt like both the TI-Nspire document and the paper document helped them understand this. So let's continue. Let's just look at these other pages for a moment. So this one, of course, has a place where the derivative is undefined because we have what my students like to call a corner, but it's where the derivative or the slope of the tangent line, the left-hand derivative is not equal to the right-hand derivative. So we can see that the left-hand derivative is 2 and the right-hand derivative is 0.5. And so they can talk about that. We can talk about that together. The next page shows a place where the derivative is 0, but the function decreases both to the left and to the right of that place where the derivative is 0. So I feel like the students are getting a good experience with a variety of graphs here to explore. And then, of course, we have our classic sort of an absolute value graph. And so they can see that the slopes from the left are 2 and on the right are -2. And so we have a place where the derivative does not exist. I really love how the fact that the tangent line sort of disappears here. But we do have what I would call a local max at this point, a relative max. So when we go to this next page where they kind of have a summary of everything, we see lots of different things going on, and obviously this is some piecewise function, but they can identify local mins, local maxes. They can identify places where the derivative doesn't exist. They can identify places where the derivative is 0, and then they can observe their tangent line, the slope of their tangent line. So in this particular case, we're getting an x value as well as a slope. And then this is the second part of the paper document that they fill out this part of the table. And so they have these various points where interesting things were going on, and these would be critical points. And then why they are critical points. I have my students actually give why, whether f prime was 0 or f prime did not exist, whether it's a local min, local max, or neither. And then when they describe the sign change in this part of the table in that right-hand column, they finally had a good summary of what was going on. Then I really like the fact that at the end we're actually going to write out what will be their first derivative test and talk about the first derivative changes signs from positive to negative, then f of a is a local maximum, and then likewise with the local minimum. And if it does not change signs, then f is neither a max nor a min. Okay, Steve, I'm going to pause. Do we have any questions, or do you have any input there on that particular one?
Vicki, I have one. If you could go back to that activity just for a second.
Okay.
Can you bring that back up on the screen? I think I just wanted to point out one other thing. Can you go back to page 1.4?
Yep.
I think this is a nice example of something that ties in with what I talked about. Let's just suppose that function, goes off for on and on forever and ever down to minus infinity on the right-hand side and plus infinity on the left.
Okay.
Right where you have that x value right now, the tangent line is horizontal. Let's suppose. I mean, it looks like that. Its slope is 0.
Yes.
Okay.
Yes.
So I would say then that this function is decreasing over the entire interval, minus infinity to plus infinity. So I certainly wouldn't split that up into two parts. I wouldn't exclude that value of x, whatever it is, like is it x equal 2? So that's a good example, one that I didn't cover, of course, but that function is decreasing over the entire interval.
I agree.
Thank you.
And okay. All right, so then another document. I've got 4 documents. I think we'll have time to look at all of them. So the next one is a second derivative analysis. So now I would like to get into more. So my students have worked with first derivative test. We've talked about where a function is increasing or decreasing based on the sign of the first derivative. So now we're ready to get into what the second derivative tells us. And so this is a second derivative analysis document. On this one, it looks similar to the derivative analysis, but is pointed directly to the second derivative. So we have that same graph, and this is just sort of a review screen. So this would show us where the function is concave up. This would show us where the function is concave down. It's a good reminder if they've forgotten that from when we worked on the earlier document. And now we're going to drag a point across. So what I like to talk about here is the connection between what is going on with the slope of the tangent line and the concavity. And so this is one of those times where I'll say, everybody watch, let's talk about what happens as I drag this point from left to right. And so we can clearly see that the tangent line is above the curve. So we see concave down. That's very clear from what Steve talked about. But I noticed something else happening. I can see that those values for the tangent are decreasing. And so if you recall, Steve pointed out that when a function is concave down, its derivative is decreasing. And so this is why the slopes of the tangent lines are decreasing. Now, it's a little hard to see. Let's see, we're going to get a point of inflection somewhere about right here, and then suddenly we're going to watch those slopes start to increase. And so I'm talking about increasing, decreasing with my students actually looking at the numbers, what the slope values are that are on the screen. And I think that's a really good connection for the students to make. And then, of course, we're going to change now, and our slopes will start decreasing and we're concave down. And then likewise, our slopes will start increasing and we're concave up. There's one more page, I think, and one more little part here. And on this one, it's sort of tying it together that not only is this where we would say that the function is concave up, but it is where f prime increases. And then this is not only where we would say that the function is concave down, but it's where f prime decreases. So I primarily use this document to emphasize the derivative, the first derivative decreasing, increasing, and that connection to the concavity of the function. And then my last document that I usually use with my students, and Steve, let me pause one more time. Do we have any questions or anything that we need to address? Okay.
I don't see any here.
Okay.
Michael maybe has some, but I don't see any, Vicki, yet.
No,
Okay.
I think there's a side conversation in the chat window about, for instance, like x cubed, as far as whether it's okay to split up x cubed into 2 separate intervals, or like Steve, like you had mentioned, that would be strictly increasing or strictly decreasing depending on what the sign of the function is.
Okay, so y equal x cubed to me is increasing on the entire interval, minus infinity to plus infinity.
do you think it's wrong if it's written as two separate intervals where 0 would not be included in that?
So if that were an AP calculus question, I'm just going to guess. And don't quote me on this one. Don't record this one, Michael. I would say that would not be marked wrong, but in my opinion, that's increasing over the entire real line.
And can I also maybe suggest that there's probably a good chance that the College Board would probably try to avoid that situation, right?
Absolutely.
Okay.
Vicky's more qualified to answer that than me, I think, but yes, I would say so.
We definitely talk about that when we're, talking about questions and what we, preliminary grading standards and things of that nature. So it definitely is discussed and what we will accept and not accept. But I think that we would try to avoid something like that. But I'm sitting here thinking about that. Go back to like an Algebra 2 teacher or even a pre-calculus teacher when they're looking and talking at the graph, or talking about the graph, the cubic function y equals x cubed. I think they're probably going to talk about it as an increasing function without getting into any kind of interval notation, but just in general describe it as an increasing function. So, that kind of makes it an interesting thing that goes on when the students move to different levels of math classes throughout high school, too. All right, so let's look at this last document, and this is just, again, I'm just trying to give the students a lot of visuals. I'm a very visual learner, so maybe that's why these things help me a lot. But I think if students have a vision of something they've seen in the classroom that they can sort of put their hands on or be reminded about later when you're reviewing or when something comes up in class a month later after you've finished this topic, that they've got something to sort of connect to. And sometimes I'll actually pull these documents back up and say, remember when we looked at this, or remember how this works. So concavity and slope of the tangent line. So in this case, I think I might have kind of written this one. I'm not even sure anymore. I kind of lose track of things. I think I tried to take the first derivative test one and just change it up a little bit so that they could see a clear parabola that is concave up. And now we don't have things sort of jumping around. We can clearly watch this slope and see that this slope is increasing over this entire interval and clearly see that the tangent line is below the curve. So that was sort of the main point of this document, is clarity as far as what the students were exploring and looking at. So if I look at page 1-3, I wanted to clearly give them a parabola that opens down so that it's concave down. The other day I had a student that had a light bulb moment that was like, oh, you mean when my algebra teacher was telling me the parabola was opening down, she really meant concave down? And I went, oh my goodness, yes. So it was sort of interesting. So clearly they can see the tangent line above the curve, and we can clearly see that slope of the tangent line is decreasing. And then I decided to put Mr. Cubic of some sort of cubic here, and so we can watch the slope of the tangent line, and those slopes are first we kind of have concave up, so first they were increasing and then decreasing. So I've sort of made a gradual move from the parabola to the cubic, and then I decided I wanted a cubic that was a little more exciting, and so now we can clearly see tangent lines above. And if you can get it just right at the point of tangency, you can kind of get it where the kids can see that there is a place on the graph where, I don't know what that strange little extra dot is that was showing up, but a place where the tangent line is sort of half above and half below. So we talk about that a little bit. And so now the tangent line, let me grab the right thing. So now my tangent line is below. Some places when you're really close to the point of tangency, it's hard to see what the tangent line is doing. I mean, not the point of tangency, the inflection point. I might have said the wrong thing a few minutes ago. But in this case, we can see that the slopes are increasing again. So my apologies if I misspoke while I was talking about that. Okay, Steve, do we have any questions on this?
I don't see any. Vicki, Michael?
The only question I just saw pop up was from Chris, and Chris was curious as to whether it can be argued that critical numbers are where the derivatives are zero or undefined, and that a function isn't differentiable at an endpoint.
Well, certainly the critical points, the critical values are where the function, where the first derivative is zero or does not exist. That's a pretty standard definition, I think. And then what was the second one about endpoints, Mike?
I think Chris is just wanting some clarification on whether or not those critical numbers or critical points on a closed interval can include, if they could be the endpoints or not, if those endpoints could be critical numbers.
No, I consider those, I think of those as separate in my analysis. An endpoint is separate. I'm thinking about an analysis for looking for example, absolute extreme values. So I would find the critical values on the interior of the interval and then take a look at and evaluate the function at the endpoints.
Same thing. My definition of a critical number or critical point is an interior point in the domain. So if it's a closed interval that's your domain, then the critical number or the critical point has to be an interior point. I mean, I joke with the kids and say it's got to be in a little neighborhood, and you got to have neighbors on both sides. And if you're at an endpoint, you don't have a neighbor on the other side. So I mean, that's kind of our little inside joke there. But it's getting them to think about there's got to be an interval about that critical number for it to become a relative min or relative max, or even a neither relative min nor max. And I think that's probably what we're leading up to.
In connecting this with something we talked about a little bit earlier too, I think that question, Mike, is something that the College Board would avoid on an AP exam. So I don't know if you would see a question where a place where the first derivative is zero or does not exist would also occur at the endpoint of a function, at the endpoint of an interval, excuse me. And then a question would ask something like, well, where are the critical values? I don't think you'd see something like that to avoid possible conflicts with definitions in certain textbooks.
And a lot of times those questions are worded on the open interval. On the open interval, where do you have, where's the local minimum located, what's the x-coordinate of a local minimum in that open interval? And that's a way to avoid those endpoints.
Yep, good point.
So just very quickly, and I am on a CAS machine. My students do use the TI-Nspire CAS in the classroom. But in case you didn't know this, I'm going to very quickly put I'm going to put up a new document, and I'm going to select graphs, and I'm going to graph the function that Steve had in his presentation, which was x to the fourth minus 4x cubed, I think it was. 4x cubed. Oops, I left the minus sign out. Yeah, that's going to be a little bit of a problem there. Okay, so we have this, and just to quickly get something here, I think it was negative 27. So if I go to negative 30, we should be okay there. I'm just going to move that out of the way for just a second. So if you did not know this, I'm sure you know that with this particular device, you can locate your relative mins and relative maxes. So under menu, we can go to analyze graphs. And in this case, we might want the coordinates of the minimum. And so I need a lower bound and an upper bound. And sure enough, there's that minimum, 3, negative 27. Students will never be able to do this on the AP exam. They won't have this technology available if they were looking for something like this. But I think it's a good tool for students to check their work. Then mine were amazed that if they went to menu, analyze graphs, oh, look, there's inflection. And so we could look for our inflection point, and there we have it at 0, 0. So I've tried to get my students to do the analytic work, paper, pencil work, and then check your work. Don't come up to me or call me to your desk and say, is this right? You've got technology, so check it with the technology. So that's pretty much what I have to share with you with technology. So Steve, have you got anything to add to this graph I have here that you might want to talk about, or any other part of the technology that's not connected to one of those prepared documents?
I think you made a good point, Vicki. I still like to use the technology to do two things: to explore, so I kind of know what I'm shooting for example, in terms of increasing or decreasing or concavity. And then once I work it out analytically in my class, I use the graph again to confirm my results. So I really like I like the CAS version too.
Okay, that's very similar to what I do also. Okay, Mike, it looks like we're about done here. So I need to quit sharing my screen and pass you control. Except it won't. Yes. Okay, I had to answer a question. There we go.
Thanks so much. Thanks, Vicki and Steve, for everything you shared tonight. If you do have any last-minute questions as we're wrapping things up, please try to get those asked. I know they'll try to get those questions answered. I do want to share a couple things available on our website, education.ti.com. A few people have been asking about the TI-Nspire and where to get that trial version if that's something that you're interested in. One way to do that is on our webpage under Products. You can find TI-Nspire technology, and say you're looking for the teacher software, like Vicki was just talking about, the TI-Nspire CX CAS teacher software. If you click on that and scroll down just a little bit, there's a try it for 90 days, and then after that you could make some decisions. We're looking forward to the T-Cubed International Conference coming to Baltimore early March this coming year. It's a great place to meet people like Steve and Vicki and attend sessions that help sharpen your skills in calculus and with different pieces of technology. And it really is a great place for me to connect the technology, the content, the pedagogy, and again to make lifelong friends and be with common-minded people. So please feel free to learn more about the conference on our website, education.ti.com. We're currently running an extra credit contest for teachers, and if you visit tiextracredit.com, you can learn a little more information about what's entailed as far as some of the prize giveaways and when those giveaways happen. But the bottom line is that as you do certain things in your classroom, you can visit that tiextracredit.com website, and you can earn entries. And by earning more entries, you increase your odds to win some of those prizes. So doing things like tonight, like attending a webinar, will get you additional entries. And there's a specific code that you can use for tonight's webinar, and that specific code is end of the line. It's not case sensitive. I am putting it in the chat window, and it's one word. End of the line. Again, please feel free to visit tiextracredit.com to learn more. To receive a certificate of attendance for tonight's webinar, go ahead and click the link in the chat window. Also listed is a link for the documents that were used by Vicki tonight. And if these aren't working for any reason, feel free just to hang tight. You'll automatically get a follow-up email in a couple days. That follow-up email will have a link to the recording, a link to the certificate, and a link to the documents as well. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Steve and Vicki, for everything you shared tonight. We really appreciate it.
My pleasure, Mike. Thanks.
Enjoyed being with everybody tonight.
And thanks, everyone, for joining us. We hope to see you back online real soon. Have a great night.